The hybrid orbital diagram that follows presents the final step in the formation of hybrid orbitals by silicon atom. What type of hybrid orbital is produced in this hybridization? All right, so what they've done is they promoted an electron from the 3s up to the 3p to get 4 half-filled orbitals, and now they're going to mix all 3 p's with the s to make 4 hybrids. What I don't like about this drawing is that they're not showing that the 3p is a different potential energy than the 3s. So when I mix the 3p half-filled p orbitals with this half-filled 3s orbital, I make 4 hybrids. 4 atomic orbitals makes 4 hybrids, all the same energy, all different energy than either a p shape or the s shape from which they were made. So sp3 hybridization. Shown here are 3 pairs of hybrid orbitals, with each set at a characteristic angle. For each pair, determine the hybridization, if any, that could lead to hybrid orbitals at the specific angle. So guys, this is the way we figure out what the hybridization of the molecule is. We look at the geometry. So if you have a 109.5 degree angle, 109.5 degree bond angle, you're talking about a tetrahedral geometry, and that indicates sp3 hybridization. That'd be the same with bent geometry with 2 bonded pair and 2 lone pair, or 3 bonded pair and 1 lone pair. sp3 hybridization. The 120, that would deal with a planar trigonal geometry, and that's sp2 hybridization. So anytime you see a planar trigonal geometry, it's sp2 hybridization. And again, we talk about sp3 or sp2 hybridization. It's the geometry of all the electron pairs. Now 90, this could indicate sp3d or sp3d2, right? Because we could be talking about the relationship between the fluorines. We could be talking about not the fluorines in this case around the ring there. They're 120 to each other, but the fluorines on the inside inside of the bipyramid would be 90 to the ones that are representing the points of the pyramid. So seesaw shape, T shape, trigonal bipyramidal are examples of sp3d hybridization. Polypropylene, C3H6, is a gas that is used to form the important polymer polyethylene. Its Lewis dot structure is blah, they give it to us. A, what is the total number of valence electrons in the polypropylene molecule? All right, so we figure that out by just adding them up, right? You've got 3 carbons and 6 hydrogens. So each carbon donating 4, so that's 12 valence electrons from being donated from the 3 carbons. 6 electrons being donated from the 6 hydrogens, a total of 18 valence electrons. How many valence electrons are used to make sigma bonds? Well, anytime we have a single bond, or 1/2 of a double bond, that's a sigma bond. So a sigma overlap, overlap within the internuclear zone. So we have 1, 2, 3, 4, 5, 6, 7, 8 sigma bonds. C, how many valence electrons are used to make the pi bonds in this molecule? Double bond is 1 part sigma bond, 1 part pi bond. So 2 electrons account for that true double bond between carbon number 1 and carbon number 2. D, how many valence electrons remain in non-bonding pairs in the molecule? Well, this one has no lone pairs. E, what is the hybridization for the carbon atom in each molecule? All right, so get used to looking at the Lewis dot structure and recognizing what the geometry would be. So if I have 3 bonded pair, and we count double bonds like we do single bonds in terms of repulsivity, we have a planar trigonal geometry around carbon number 1. So that's an example of sp2 hybridization. We'd also have a planar trigonal geometry around carbon number 2. That would also be sp2 hybridization. And we have a tetrahedral arrangement, right? 4 bonded pairs, no lone pairs around carbon number 3, that'd be sp3 hybridization. '79, what does the term diamagnetism mean? Diamagnetism means when you have all the orbitals of the molecule paired, and this molecule would therefore be relatively unaffected by a magnetic field. Paired electrons spinning in opposite direction cancel each other out magnetically. B, how does diamagnetism of the resubstance, well, we answered that with A and B. C, which of the following ions would you expect to be diamagnetic? All right, so this is when we're dealing with the molecular orbital model, right? Instead of half-filled orbitals overlapping to form sigma bonds and pi bonds like we have with the localized model, the molecular orbital model is something totally different, right? It's an overlap of the orbitals, and you end up with bonding orbitals and antibonding orbitals. So I would suspect that oxygen 2- and beryllium 2- would be candidates for being diamagnetic. And the way we do this is by looking at their electron configuration. So looking at the beryllium 2+ first. Oh, was it 2-? Yeah, it was 2+, I'm sorry. 2+ first. Beryllium usually has 4 electrons to be donated to the molecular orbitals that we create when we overlap, or we blend with the atomic orbitals of the other atoms. So right now I'm looking with these black boxes, we're looking at the atomic orbitals for the 2 beryllium atoms. So we've got beryllium 2+, so an electron's been taken out of each of the beryllium atoms that are going to make this molecule. So we have 6 electrons to account for. When we blend 2 1s orbitals, we end up making a 1s sigma antibonding orbital and a 1s sigma bonding orbital. Right? The bonding orbital has a lower potential energy than the 2 atomic orbitals from which it was made, and the antibonding orbital has a higher potential energy than the atomic orbitals from which they were made. Right? Constructive interference of the wave that represents the orbital would lead to the bonding orbital, right? The lower potential energy, the antibonding orbital being destructive interference. So anyway, overlapping these 4 atomic orbitals, you make 4 molecular orbitals. So the 1s bonding and the 1s antibonding are lower in potential energy than the 2s sigma bonding and the 2s sigma antibonding orbitals. So those 6 electrons would want to be in the lowest potential energy spot first. So diamagnetic, right? When you put the electrons into this electron configuration, they're paired. So this is the definition of diamagnetic. Paired electrons in the molecular orbitals. If you do the same thing with O2-, in this situation, you've gained 2 extra electrons, right, to the electron configurations for the 2 oxygens. So each of these oxygens I've represented as having an extra electron, right? Usually instead of having 6 valence electrons to donate, they've got 7. So these 14 electrons would have to go into the sigma bonding and sigma antibonding and pi bonding and pi antibonding orbitals that are created when you overlap these orbitals. So it's just putting electrons into these electron configurations, right? So the electrons, those 14 electrons would want to be in these orbitals, these lowest potential energy orbitals, and we end up with, again, paired electrons, diamagnetic.